So today we're going to take our first formal look at a system, which is new to us in terms of a formal analysis, but it's something with which we are already familiar in the course, namely the very famous problem of the simple harmonic oscillator. Just a few reminders for you. The potential V of x that goes with the simple harmonic oscillator is this nice simple quadratic potential, which I've sketched here for you as a function of x. That potential is traditionally written down in terms of the constant, the spring constant, 1/2 kx squared, but more conveniently for our analysis, as we will see, which will make the math come out a little bit easier for us, it's more common in quantum mechanics actually to write the spring constant down in terms of the frequency as m omega squared. In fact, if you insert the fact that the natural frequency omega of our oscillator is root k over m and insert that into this expression, you can quickly see that it's really the same thing. Now, once we have this potential in place, of course, that gives us a Hamiltonian, which would then be the kinetic energy plus this potential energy. And corresponding to this, then, we will now have our time-independent Schrödinger equation to solve for the bound states, or for all the pure states of energy, actually, which will then take our familiar form, where we have not only the kinetic energy operator, but also the potential energy operator, acting on our bound state wave function, giving us back then the energy times our bound state. Now notice I'm referring to all of the pure energy states here as bound states. And the reason for that is that no matter what your energy level is, as you go further and further away from the origin, eventually this ever-increasing harmonic potential will become greater than your energy level, so you will indeed have classically forbidden regions both going out towards plus and minus infinity, making it the case that all energy states, no matter how high your energy, will actually be bound states. Excuse me. Now, there are a number of reasons why this is such an important system for us. As we commented when we first looked at this system in the informal portion of the course, it is really a ubiquitous system. After all, any mechanical system, as you know, near its equilibrium, you can expand the potential near that equilibrium point, where the potential must be a minimum, which is the definition of the equilibrium point, and it will always sufficiently close to that minimum look like a harmonic potential, and so therefore close to its minimum energy configuration, almost any mechanical system will behave like a simple harmonic oscillator. So they're very important for mechanical systems. But that's not the only reason why this is such an important and beautiful system. As we are about to see, this system has some very special symmetries associated with its Hamiltonian. And there's a mathematical framework that goes along with that symmetry. And it turns out that we use this very rich mathematical framework not only to analyze the harmonic oscillator in its ubiquitous nature for all mechanical systems, but also it forms the same mathematical basis that we use to study much more rich and complex oscillatory systems in quantum mechanics, namely systems involving waves. So the math that we're going to build up as we solve this problem is really worth our while, because it is the same mathematical operator type framework that is used when we perform quantum mechanical analyses of electricity and magnetism and to find operators then that correspond to this quantum concept known as a photon. You will notice that so far in this course we have really been focusing in the formal portion on particles and not so much on photons. That is a topic that is rather rich and generally comes up only in your more advanced undergrad or even first semester graduate quantum courses, but by going through this analysis using this operator approach that I'll be showing you, you will be well on your way to understanding the quantization of the electromagnetic field as well. Now, just before we really dive into the analysis, I'd like to remind you that, of course, we have studied this system previously from the perspective of Bohr-Sommerfeld quantization, where we found that the energy levels should be some integer or non-negative integer n times this interesting quantity h bar omega, where n then would never be 0, right? N actually starts at 1 when you do the Bohr-Sommerfeld analysis and counts up 1, 2, 3, and so forth. So one of the things we hope to get out of our formal analysis is to get a spectrum that should look something like this Bohr-Sommerfeld spectrum, but clearly this is just really a semi-formal analysis. We're looking forward to seeing what the true result actually should be. Now, as we begin to think about carrying out the formal analysis of our time-independent Schrodinger equation, one of the first things we would do, of course, would be to isolate the derivatives on one side of the equation to see if we can come to a quick solution to the problem. I've done that for you here, but you will notice this is going to be a much more complicated type of differential equation from what we've seen before. In the past, our potentials were always constant in pieces, right? It'll be constant for a while, it might have a step in it, but everywhere it has these pieces that are constant, which then resulted in an equation that was fairly easy to solve as some kind of an exponential. Now we notice when we take the second derivative of our function, we don't just get our function back again times a constant, which would then give us these exponential solutions. Instead, it comes back times x squared with some constants. So this is a much more difficult differential equation for us to solve. Now, there are really two broad approaches to this. We can bring out the full power of our toolkit from the theory of differential equations and go ahead and solve this equation using very powerful methods such as power series methods. I, however, want us to take in this course a different type of an approach. This approach that's going to exploit this interesting hidden symmetry that this Hamiltonian in our problem has. And the exploitation of this special symmetry, as I've said, will lead us to some very powerful mathematics that will actually make solving this rather difficult power series method very efficient. And moreover, I want to spend the time to do this because it will lay the groundwork for future developments in your formal training in quantum theory, in particular how to deal with quantizing things such as the electromagnetic field and getting at the issue of photons.